everybody with me here? Alright, derivatives is very simple now because it's just a power rule derivative. So we would have dv dx, or we could call it v prime, I guess. We get 27 minus 3/4 x squared. Okay, so this is our derivative. To find a maximum or minimum, we want to take our derivative, set it equal to 0, do a sign line, look for a place where our derivative changes from positive to negative. So we're going to set this equal to 0. That's going to give us 27 equals 3/4 x squared. We're going to divide by 3/4, which is the same as multiplying by 4 over 3. So that 3 and that 27 could reduce with 9, 14 plus 36 equals x squared. We'll square root both sides, and x equals plus or minus 6. Now, if we think about the situation, does it make sense to have a negative number when we're talking about x here? That would not make any sense, right? You can't have a negative length of a side. So, really, we only want to use the 6, which tells me 6 is probably the answer. And if this problem was multiple choice, and I saw 6 there, and I was short on time, I'd just pick 6. But we do want to verify that 6 is in fact a maximum and not a minimum. So to do that, if we put our sign line, I guess let me call that as dv dx. I'm just going to start at 0 because we can't have negative numbers go up to 6. So if I pick a number between 0 and 6, 1 would be the easiest. You're going to get a positive number there. And then if you pick a number bigger than 6, like 7 or 8 or 10, 10 is probably the easiest to do. 27 minus 3/4 times 10 squared, which is 100. So that's 27 minus 75. That's negative there. So if this was free response, we would need to say since dv dt changes from positive to negative at x equals 6, the volume is maximum at x equals 6. And it does ask what dimensions will produce the maximum volume here. So 6 is the length of the sides. I do need to know the height. So the height, I have to go back to that surface area formula. So that surface area formula was 108 equals 4xh plus x squared. We've already found x is 6, so we have 108 equals 4 times 6h plus 6 squared. So 108 would equal 24h plus 36. We would subtract 36, which would give us 72 equals 24h divided by 24, and h equals 3. So we would have 6, is this feet, inches, what is this? Inches. So you would need a box that was 6 inches by 6 inches by 3 inches. This is something that I could see definitely actually happening if you worked for a company that was like packaging things, if you were designing packages. Maybe not this particular instance. I could actually see it the opposite direction, more likely where you have a certain amount of material to work with, like you've got a sheet of cardboard that is 8 inches by 10 inches, and you want to make a box out of it that has maximum volume. So that might be something that you want to do. Although sometimes I'm pretty sure some marketing companies do the opposite, and they want their package to look a lot. They want surface area to be maximum, but volume to be minimum, so they don't have to put as much stuff in it. So if you have, like, for example, I was telling you, like, anything cone shaped is always sort of a ripoff, because a cone is only a third of a cylinder. So if you have like a cone shape, then it's a third of what it would be if it was just a cylinder. But it looks almost as big as the cylinder when you just look at it with your eyes. And of course, marketing, geniuses take that into account whenever we see that this cereal box looks bigger than this one over here. We think that there's more in it, but there might not actually be, which is trickery. And also probably bad for the environment, because they're using more packaging material just to trick us into thinking that we're getting more there. So my brother-in-law works. He works in marketing, and I tell him sometimes that it's manipulation. Like, I'm pretty sure that my phone listens to me. Like, I could tell you that I need a new spatula right now, and I would go to my phone, and like the next ad that pops up would be for a spatula. I don't even have to Google spatula. I know if you Google spatula, you're going to get spatula ads, but I think it's listening to me sometimes, because it's just something I've talked about, and then I get ads for it. So I think it's manipulation. My brother-in-law would say that it's good marketing. It is delivering the product that you most need or want right to you. So I guess one or the other. All right, for example 2. This is more of a math example. This is not much of an application here. Although there could be design elements that you might want to know something like this for. But it's been simplified down just to the bare bones for this problem. So we want to know which points on the graph of y equals 4 minus x squared are closest to the point 0, 2. So for this problem, it's going to be helpful if we make ourselves a graph of this, so we can sort of picture what is happening. Okay, so let's graph this one. This one is a pretty easy one to graph by hand. This is just an upside down parabola that has been moved up 4. So we just need 1, 2, 3, 4, 1, 2 over here on the x-axis to get what we really need. So we would have these points here. And then our parabola would look like this. Here. So those graphing skills we learned in pre-cal, they're coming in handy here. We can see what this looks like. We want to know, notice it says points on the graph that are closest to the point 0, 2. So that's this point right here. So let me lock this in place so that I can erase things on it. Alright, so what you got to decide, we could look at it, maybe these points are closest. Or are these little lines right here shorter? Or maybe this little line right here is the shortest. I do know, because of the symmetry of this, that there's going to be 2 points. Because that point that they're asking us about lies right on that axis of symmetry. So the closest point is going to be on that line of symmetry. You're going to have 2 points on either side for this one. Now, if my point was maybe like over here somewhere, then I would only have one, because it would definitely only be on this side. I'd have several different possible options there. So I'm going to erase that so we can see it a little bit better. So we want to know which point is the closest. I'm just going to use a point over here, and I'm going to call this is the point 1, 3, but I'm going to call it X, Y, because I don't really know what points it is. I guess I could make it. Actually, let me put it right here. I'm going to put this red point right here. I'm going to call that point right there X, Y. Okay, it looks pretty close, but I don't know its exact coordinates. It might be at 1, 3, but it might be a little below it. I can't really tell. I don't think it's above 1, 3. And this point, I know the coordinates of it are 0, 2. So, how do we find the distance between 2 points? Anybody remember that formula? I had a square root. Yep. And distance formula has a lot of flexibility in it. If you got the x's first instead of the y's, that's fine. If you put the x1s before the x2s, that's fine, because it doesn't really matter as far as the signs go. But this is our distance formula. So let's do distance formula with these 2 points. So our distance formula would be y minus 2 squared plus x minus 0 squared. So, just like our last problem, we've got a formula now. But the problem with this formula is it's got an x and a y. And if I take the derivative of it, then I'm going to have dy dx's, and I'm going to have variables that I can't solve for because I've got 2 variables. So I can't do this as it is currently, because I need to just have 1 variable. So in the last problem, we had to create an equation to use. We don't have to do that here, because y is the y coordinate right here. I also am told that y equals 4 minus x squared. So if y equals 4 minus x squared, I can replace y with 4 minus x squared. So I'm going to do that. So I've got 4 minus x squared minus 2 squared plus, I'm just going to write this as x squared here. And so that's going to be 2 minus x squared plus x squared. And because we're going to have to take a derivative, it's going to make our life a little bit easier if we go ahead and simplify it, like multiply this out and simplify it. So I will get 4 minus 4x plus, 4x squared plus x to the 4th. So I'm just doing square, double, square there, plus x squared. And so x squared, right, I'm sorry, that last one shouldn't be a square. No, it's right. It's right, never mind. I've got, but the way I'm writing here, I want x to the 4th minus 3x squared plus 4 there. I've got my formula for distance. It's all in terms of just x, so that's good. What's bad about this is I've got that square root, which means that my derivative is not nearly as easy to take as the derivative for the last problem, right? I would have to use a chain rule, and I've got all of that stuff, and it's going to be kind of hard to figure out what the critical values and stuff are. However, if, let's just look at this. Let's pull it up on Desmos here. I think that'll be our easiest way to look at it. Let's look at this. Y equals square root of x to the fourth minus 3x squared. What was that last number? There. Plus 4. Okay. Alright, so if I have this graph right here, the minimum points are right here. So now if I had Desmos, I could just graph this, and I already know that 1.225 is the answer for my x. But I don't have Desmos, and I'm not going to on the exam. So, and this one probably is not going to be calculator active on the exam. So that strategy is not going to work. However, I do want you to look at this. Y equals x to the fourth minus 3x squared plus 4. Okay? If I look at that graph, it's a different graph. But what do you notice about those minimum points? Their x-coordinates are the same, right? So the x-coordinates are the same, which is all I really need right here. So if you're taking the square root of something, the minimum of what's under that square root is going to be you're not going to have the same minimum value, but it's going to occur at the same x value. So what we can do to make this problem a little bit easier is we can say if f of x equals x to the fourth minus 3x squared plus 4 has a minimum, at x d has a minimum at x. Now you could not necessarily do this with everything, but with the square root, or if you had something squared or to the third or fourth or something, that third might not work with the negatives, but this will work. So rather than looking at d, I'm just going to look at the derivative of f. So f prime of x would be 4x to the third minus 6x. And then I can set that equal to 0. So I would have 2x times 2x squared minus 3 equals 0. So 2x would equal 0, which would just give us x equals 0. And then I would have 2x squared minus 3 would equal 0. So 2x squared would equal 3. X squared would be 3 halves. And so I would square root both sides. So x would equal plus or minus the square root of 3 halves. So if I put that on a sign line, negative square root of 3 halves, 0, and positive square root of 3 halves, and I've got 2x and 2x squared minus 3, and I want to know what f prime of x looks like. 2x, that's negative for anything below 0. It's positive for anything above 0. Negative square root of 3 halves, that's like negative square root of 1.5. So that's going to be smaller than 2. So like negative 2 I could plug in. If I plugged in negative 2, 2 times negative 2 squared minus 3. 2 times 4 minus 3, so 8 minus 3 gives us 5, which is positive. A number between 0 and negative root 3 over 2, that could be like negative 1. So 2 times negative 1 squared minus 3, that just ends up being 2 minus 3, which is negative. This one's negative, this one's positive. We go through and check those. So I end up with a negative, positive, negative, positive for the derivative. And so when the derivative goes from negative to positive, that means I have a minimum point, because negative to positive would be decreasing back to increasing, so that'd be a minimum. Right here, I also am going to have decreasing to increasing, so I'll have a minimum there as well. So you have minimum points at both of these x coordinates. And I am not going to take the time, but especially since you get square root of x, square root of 3 over 2. If you needed to know, this one in particular asks for the points on the graph, so you would need y coordinates. I am just going to look over here at Desmos and tell you that it's 1.75. So instead of working it all out, to find it, you would have to go back up to the original problem, the D equation, and you have to plug in square root of 3 over 2. I am just going to tell you that your answers end up being square root of 3 over 2, 1.75, and negative square root of 3 over 2, 1.75. So if we go back to the original equation, if we look, we had f of, sorry, so we just have y equals 4 minus x to the second. And so if we graph the point square root of 3 over 2 and 1.75, because I didn't have square root, plus its square root 1.75. It's not working. Oh, no, we would have to plug into y. I'm sorry, not distance. That's 1.7, square root of 1.75. That is your distance. We would need to, or 1.75, I guess, is your distance. We would need, if we're given the coordinates, we need to plug into y. Let me just do this so that we're doing it right. We need to plug into y to find those y coordinates. So we would say y equals 4 minus square root of 3 over 2 squared. So 4 minus 3 halves, which is going to give you 5 halves. And my square root should go all the way down here. And it's going to be the same even if that's negative. So let me try that again. Let's make this 5 halves. And so these points on the graph right here, they are the absolute closest point to the point 0, 2 in the graph. Questions on those? There's a lot of applications that this could apply to. This is a pretty boiled down question, but you know, there could be lots of reasons why you would want to know the closest point. For example, if you had some sort of building design and you're wanting to put a brace here, you want to use the least material possible. If this were like a shoreline and you were going to swim to shore, you would want the shortest route possible there, or if you had like a shipping lane or something, lots of things you could do there. Okay. In reality, shorelines typically are not parabolas, though they're much more difficult. Okay, questions? Okay, let's look at another one. A rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are to be 1.5 inches, and the margins to the on the left and right are to be 1 inch. What should the dimensions of the paper be so that the least amount of paper is used? So, in this case, this would be something that might need to be used if you were producing something at a large scale, right? Obviously, if your teacher tells you just put 1.5 margins at the top and bottom and 1 inch margins at the left and right, you're just using regular paper. You're not doing something like this. But if you are producing some sort of maybe marketing pamphlet or something, and you want a border around the edge that it's a 1.5 inches at the top and inches on the side, and you want to use as little paper as possible, then you would want to get those dimensions right. Because if you make it too tall and skinny, that's going to use more paper. If you make it too short and fat, it might use too much paper. So we're going to have to figure this one out. Again, you're probably not going to really care if you're running off 100 flyers for Vacation Bible School. But if you are producing something very large scale, so you're producing like say you work for a politician and you are sending out like mass marketing things in the mail to, thousands and thousands and thousands of people, then this might be something you might be concerned with for something like this. So we have our rectangular piece of paper, and we know for sure that we have 1.5 inches at the top and bottom of the page, and we have 1 inch on either side of the page for our margins. So we would know that this is 1.5 inches right here, and we would know that this is 1 inch right here. What we don't know is we don't know the dimensions of the paper. Or, let's see, we don't know the dimensions of the print. Now, you've got a couple options on this, because we know that the dimensions, we have to have 24 square inches of print. We know that we want to find, if you look at the question, that'll help you decide where to put your X. What should the dimensions of the paper be so that the least amount of paper is used? So the dimensions of the paper, we're looking for this, we'll call that X, and this, we'll call that Y. So you could let this be X and Y. It is also possible to do this problem by calling this part X and this part Y. So you could do it either way. The only reason I'm choosing this way is just because once I solve for X, that gives me the answer for the problem. Whereas if I do this, then I've got to add to it. Okay. So, but what I know is I know that this area here, the print area, I know that that is 24 square inches. So I know about the dimensions of this area. I know that this length times this length has to give me 24. So using x and y, x is this whole side right here. What would the length of this horizontal side right here be? It's going to be x minus 2. Why 2 instead of just 1, Lily? 1 inch on each side, right? So then, this part right here is going to be y minus 1.5 because we're, going crazy. Let me ignore that. There. I gotta make it even go away. Okay. Try to. Okay. Try to ignore that. It's not cooperating. So, I know that x minus 2 times y. Did I write 1.5 there? I did, didn't I? It should be 3. Did I say 3? I meant 3. 1.5 on each side, top and bottom. So y minus 3. I know if I multiply those together, I get 24. Okay, so we've got a formula set up here for that inside area. And so, okay. Oh, no. Hold on a second. We've got to make. Hold on. Okay, yeah, we know this is true. Okay, what are we trying to minimize? I've done it here different than I did on my paper, and I thought I've done it wrong, but I haven't. What are we trying to minimize? The total amount of paper, right? So the area of the whole piece of paper. So what we want to minimize the total area. And for that total area, we would just do x times y. And so that area formula, that's what we need to take the derivative of. But right now it's got an x and a y, so we can't do it. So we've got to solve this equation for either x or y. It does not matter which one. Let's just pick one. Lily, which one do you like, x or y today? Okay, so let's solve for y. So I'm going to divide by x minus 2. You could distribute here, but it's going to make it much more difficult to solve. So divide by x minus 2. And so y minus 3 equals 24 over x minus 2. And then you're going to have to add that 3 to both sides. So y equals 24 over x minus 2 plus 3. So, let me think for a second. I'm going to plug this in for y. Let's go plug it in. Area equals x times 24 over x minus 2 plus 3. And I really don't feel like taking the derivative of that. That looks bad. Let's try getting common denominators here. Maybe it'll clear some stuff up where it's a little bit more simple. If nothing else, we'll just have a straight quotient rule if we can get common denominators. So right now this is over 1. So I'd have to multiply by x minus 2 from top and bottom. So I would get 24 plus, if I distribute that 3, 3x minus 6 all over x plus 2. And so that gives me x times 18 plus 3x over x plus 2. And this is x over 1, so let's distribute that x to the top. So I would have 18x plus 3x squared over x plus 2. I hope this works out because it's backwards from the way that I did it. It is. Yes, let's fix that. Okay, so you've got an area formula here. What we're going to do is we are going to take the derivative of that area formula. So the ADX is going to be x minus 2 times the derivative of the top, which is 18 plus 6x minus 18x plus 3x squared times the derivative of the bottom, which is just 1, all over x minus 2 squared. And so our life will be a little bit easier if we simplify this. So here we'll get 18x plus 6x squared minus 36x minus 12. No, that 36 doesn't have an x with it. 36 minus 12x squared minus 18x minus 3x squared all over x minus 2 squared. And so that's going to give us negative, we've got, let's see, yes. Okay, so we've got a positive 6x squared and negative 3x squared, so we get positive 3x squared. And we've got positive 18, negative 18, those cancel. We got the minus 12x and then the minus 36 all over x minus 2 squared. And to make my life a little bit easier, I'm going to go ahead and factor that numerator. So 3 times x squared minus 4x minus 9 over x minus 2 squared, and then that'd be 3 times. That doesn't factor, does it? Oh, it's not 9. I'm dividing by 12. That's better. Alright, and then that will factor into x minus 6x plus 2. So that's a extensive derivative that you got to take there. Whenever we look at that derivative, we care about where it equals 0. The good thing about going ahead and factoring this is you just already have all the answers. So x equals 6, x equals negative 2, and then x equals positive 2. 2, or all the places where this derivative is either 0 or undefined. And so if we put these on a number line, we would have negative 2, positive 2, 6. Now, as much as I don't like these lengthy problems, I do kind of love doing these derivative charts. I don't know why, they're just kind of satisfying. So you got a lot of stuff. You've got 3, x minus 6, x plus 2, and x minus 2 squared. So I'm going to put all that over here. 3, x minus 6, x plus 2, and then x minus 2 squared. And then the last thing we want to know is the derivative of a with respect to x. So that derivative. So if I make a sign chart for this stuff, I just kind of like doing these. 3 is always positive. X minus 6, it's going to be negative all the way till you get to 6, and then it's going to turn positive. X plus 2, it's going to be negative for anything below negative 2, but then it's going to turn positive. And then x minus 2 squared is always positive except for when it equals 0, which is at positive 2, because you're squaring it, so it's always positive. So then if you just look down each line, if you have an even number of negatives, then you get a positive. If it's odd, you get a negative. So it's odd here, and then positive there. And we were looking, and really, I guess on this problem, I really didn't need to consider those negative values because we're talking about the length of the side of a paper. That can't be negative, so even if you did have something over here, you wouldn't include it. So minimum, that's for where we change from negative to positive on our derivative. So that's right here at 6. So, x would equal 6. And if we think about that piece of paper, if this side is 6, and we have 1 inch left and right margins, then that makes this part right here 4. That length right here would be 4. And so we know that inside part has to be 24 square inches. That makes this part right here 6. And then you have 1.5 inch margin up here and 1.5 down here. If you add those together, you get 9. So you have 6 inches by 9 inches. So you can already see, I'm sure, that these problems take a while to do because they become pretty extensive. Now, of course, in real life, you'd use a calculator for some of this, but we're not, because it gives us some good practice with it, taking derivative, using quotient rules, all of that other stuff that we need to know how to do. We're going to stop with notes right here so that